The deep sea, a place of crushing pressure, perpetual darkness, and frigid temperatures. It is an environment so extreme, so alien, that it rivals the harsh conditions found on other worlds in our solar system. Yet, despite these challenges, life persists. NASA, the agency best known for sending humans to the moon, has turned its attention to the deep sea. Why? Because studying the deep ocean offers valuable insights into the potential for life on other planets and moons. Places like Europa, with its subsurface ocean, and Enceladus, with its icy plumes, share intriguing similarities with Earth's deep-sea environments. By exploring the depths of our own oceans, we can gain a better understanding of the conditions that might support life elsewhere in the universe. It's about understanding the fundamental nature of life itself. The deep sea holds clues to these profound questions. Off the coast of Florida, submerged beneath 62 feet of water, lies Aquarius. This underwater habitat serves as a unique training ground for astronauts preparing for the challenges of space exploration. It is home to NASA's Extreme Environment Mission Operations, or NEEMO program. Here, astronauts live and work for weeks at a time, simulating the isolation, confinement, and operational constraints of a space mission. But NEEMO is more than just astronaut training. It is a platform for conducting cutting-edge scientific research in a truly extreme environment. Scientists from various disciplines join the astronauts in Aquarius, studying marine life, testing new technologies, and conducting geological surveys. The lessons learned from NEEMO have direct applications for future space missions. The depths of the ocean present challenges similar to those encountered in space. By working in this challenging environment, astronauts and scientists gain valuable experience that can be applied to exploring other worlds. NEEMO serves as a bridge between the depths of our oceans and the vastness of space. In the 1970s, scientists made a startling discovery. Deep beneath the ocean, in areas devoid of sunlight, they found thriving ecosystems clustered around hydrothermal vents. These vents, spewing superheated water rich in chemicals from the Earth's interior, create oases of life in the otherwise barren depths. Hydrothermal vents overturned our understanding of how life could exist. Before their discovery, it was believed that all life on Earth ultimately depended on sunlight for energy. But the organisms found near hydrothermal vents utilize a process called chemosynthesis. They derive energy from the chemicals in the vent fluids, not from sunlight. This discovery had profound implications for the search for life beyond Earth. The study of hydrothermal vent ecosystems continues to yield valuable insights. Scientists are learning about the unique adaptations that allow organisms to survive in these extreme environments. The organisms that call hydrothermal vents home are known as extremophiles. They are life forms that thrive in conditions that would be lethal to most other organisms. High temperatures, extreme pressure, acidic or alkaline water, and the absence of sunlight are just some of the challenges they face. Extremophiles are found not just in the deep sea, but also in boiling hot springs, acidic mine drainage, and even in the frozen wastelands of Antarctica. They are a testament to the remarkable adaptability of life. Studying these hardy organisms provides valuable clues about the potential for life to exist in other extreme environments, both on Earth and beyond. One of the most famous extremophiles is the tardigrade, also known as the water bear. This microscopic creature can survive being frozen, boiled, dried out, and even exposed to the vacuum of space. Understanding how extremophiles survive in such harsh environments can help us develop new technologies for detecting life on other planets. Exploring the deep sea is a challenging and expensive endeavor. The extreme pressure, darkness, and cold temperatures make it a hostile environment for humans. That's where robots come in. Remotely operated vehicles, or ROVs, and autonomous underwater vehicles, known as AUVs, are playing an increasingly important role in deep-sea exploration. ROVs are tethered to a surface vessel and controlled by a pilot via a fiber optic cable. They are equipped with cameras, lights, manipulators, and a variety of scientific instruments. ROVs allow scientists to observe and interact with the deep-sea environment in real time, collecting samples, conducting experiments, and exploring areas that would be too dangerous for humans. AUVs, on the other hand, operate independently of a surface vessel. They are pre-programmed with a mission plan and can survey large areas of the ocean floor, collecting data on water chemistry, temperature, and bathymetry. The development of increasingly sophisticated ROVs and AUVs is revolutionizing deep-sea exploration. Europa, one of Jupiter's 4 largest moons, has captured the imagination of scientists and the public alike. Beneath its icy surface lies a vast, salty ocean that may contain more water than all the oceans on Earth combined. This hidden ocean is thought to be one of the most promising places in our solar system to search for extraterrestrial life. The moon's surface is covered in cracks and ridges, suggesting that the ice is constantly shifting and reforming. This is likely due to tidal forces from Jupiter, which generate heat within Europa's interior, keeping the ocean liquid. The presence of liquid water, a source of energy from Jupiter's gravity, and the potential for organic molecules makes Europa an incredibly exciting target in the search for life beyond Earth. Enceladus, a small icy moon of Saturn, was once thought to be an unremarkable member of the ringed planet's extensive family. But in 2005, the Cassini spacecraft made a startling discovery: geysers of water vapor erupting from Enceladus's south polar region, spewing into space and forming a giant plume that feeds Saturn's E-ring. These geysers, originating from a subsurface ocean, provide tantalizing evidence that Enceladus, like Europa, may harbor the conditions necessary for life. The plumes contain water vapor, ice particles, salts, and organic molecules, suggesting that the ocean beneath the surface is complex and potentially habitable. The discovery of Enceladus's plumes has revolutionized our understanding of this small, icy moon. Future missions could fly through the plumes, collecting samples for analysis. Reaching the subsurface oceans of Europa and Enceladus presents a formidable challenge. Kilometers of ice stand between us and these potentially life-harboring environments. But NASA engineers are exploring a bold concept for overcoming this obstacle: the cryobot. A cryobot is a robotic probe designed to melt its way through thick layers of ice using heat. It would carry a suite of scientific instruments to explore the ocean below, searching for signs of life and studying the ocean's chemistry and physical properties. The cryobot would be powered by a nuclear reactor or another long-lived power source. As it descends, it would melt the surrounding ice, creating a liquid pathway behind it. Once the cryobot reaches the ocean, it would release an autonomous underwater vehicle, or AUV, to explore the surrounding environment. The ultimate goal of exploring the deep sea and the icy moons of our solar system is to answer the question, are we alone in the universe? To find evidence of life beyond Earth, scientists are searching for biosignatures, indicators of past or present life. Biosignatures can take many forms, from the presence of complex organic molecules to the detection of gases that are byproducts of biological activity, such as methane or oxygen. Scientists are also looking for evidence of metabolic processes, such as the consumption of energy sources or the production of waste products. Finding even the simplest forms of life on another world would be a monumental discovery, revolutionizing our understanding of our place in the universe. The search for biosignatures is a complex and challenging endeavor, requiring sophisticated instruments and careful analysis. The exploration of the deep sea and the search for life beyond Earth are not separate endeavors. They are inextricably linked. Advances in one field drive innovation in the other. The technologies developed for deep-sea exploration, such as ROVs, AUVs, and cryobots, have direct applications for exploring the oceans of icy moons. Similarly, the techniques used to search for biosignatures in extreme environments on Earth are informing the development of instruments for future missions to Mars, Europa, and Enceladus. The knowledge gained from studying extremophiles on Earth is helping us to better understand the potential for life in other extreme environments throughout the universe. The future of deep sea and space exploration is a symbiotic one. The exploration of the deep sea and the search for extraterrestrial life are not just about finding new life forms, they are about expanding our understanding of life itself. What is life? What are its limits? And how did it arise in the first place? By studying life in extreme environments on Earth and searching for life beyond our planet, we are challenging our preconceived notions about what constitutes a habitable environment and what life might look like elsewhere in the universe. The discovery of even the simplest forms of microbial life on another world would have profound philosophical and scientific implications. It would demonstrate that life is not a fluke, but a fundamental feature of the universe. The search for life beyond Earth is a journey of discovery, a quest to understand our place in the universe and to unravel the mysteries of life itself.